Hello, welcome to the 4-H Level 2 Junk Drawer Robotics course. My name is Joe Bartlett, and I'm going to be your advisor for this course. Just a little bit about myself. I am a mechanical engineer by trade. I went to school at the Missouri School for Science and Technology, or formerly known as the University of Missouri at Rolla. I have a fair amount of engineering background. My hobbies include working on cars, and one of my favorite things to do is to help my friends work on their dirt late model race cars. I have two girls in 4-H, and I really enjoy helping them work on their 4-H projects. So I really hope that I can pass some of my engineering knowledge along to you throughout this course, and hopefully you learn something about engineering and robotics. Now, before we get started, let's go over a couple of things that you're going to need for this course. So first of all, just as the name implies, this is a junk drawer robotics course. So one of the things you can start doing is start looking around in your mom and dad or guardian's junk drawer or garage or any other place where they might have some miscellaneous materials laying around, and just start gathering up those materials that you think you might want to use later on to build things with. The next thing you're going to need is a notebook. So we're going to be taking quite a few notes throughout this course. And so you can find a notebook like the one you see here at your local Walmart or Target. Or if you don't want to go buy one, you can just make one out of paper. Just get a handful of pages and put some numbers in the upper corner and maybe staple them together, and you can use that for your notebook too. Now we're going to be working out of the Level 2 robotics book supplied by the 4-H Extension Office. You can feel free to go purchase this book if you'd like to, but you don't need to. I will mention anything that we need out of the book. I'll read directly in this video, but it might be handy for you to use it to follow along. There are also some modules in that book that we're not going to cover in this video, so you may want to do those modules on your own, and if so, it'd be nice if you had the book to do those with. There are 4 modules in the book. The first module is called Get Things Rolling, and there are 4 activities that we're going to do in this module. The second module is called What's Up, and in this module, the students focus on learning a little bit about electronics. Now, we're not going to do this module in this video, but again, feel free to do this one on your own if you like. The third module is called Get a Move On. Now, there's 6 activities in this module, but we're only going to do the first 4. So activities I, J, K, and L will be the only activities we're doing. And then the fourth module is called Under the Sea ROV. And again, we're not going to do this module in the video, but feel free to do this one on your own as well, if you like. Now, one thing you're going to need for Module C is a set of plastic gears. Now, these are the type of gears you might find in a toy remote control car or something. And later on, we're going to talk about gear ratios, and we're going to use those gears in one of our projects. So I would recommend getting on Amazon and buying a set of gears. You can pick them up relatively cheap. But if you don't want to do that, you can certainly rob some gears out of an old toy or something. But if you do that, make sure that you get the gears, and you'll also need to make sure that you have the shafts that go through those gears, because you're going to need those for what we're going to do. So let's move on to Module 1. In this module, we're going to talk about friction, or more specifically, static friction. So what does something mean when we say static? Well, when we say something is static, that means that it is not moving. And we would compare this to when we call something kinetic or dynamic, or in other words, when things are moving. So when we say static friction, we mean the friction when two bodies are not moving. So what is friction? Well, friction is the force that opposes movement between two bodies that are in contact with each other. So one example of this would be the friction between your car's tire and the road. Another example of this would be when two blocks are in contact with each other. As I try to push one block one direction and the other block the other direction, there's a force that opposes this motion, and that force is called the static force of friction. Now compare this, if the blocks were sliding against each other, there's another type of friction called the dynamic friction, and that has a different value. But static friction is when the blocks are not moving against each other. There is a formula that we use to calculate the static friction. That formula is the coefficient of static friction multiplied times the normal force. So what are those two values? Well, the coefficient of static friction is a value that we develop in a lab. If you refer back to our Junk Drawer Robotics 1, scientists in a lab test and do experiments to determine what the coefficient of static friction is between various materials. And so that coefficient of static friction is multiplied by what we call the normal force. Now, what is the normal force? Well, the normal force is the force that holds one body against another. So one example of this would be a block setting on the table. So in this scenario, when the table is level, the normal force would be equal to the weight of the block in pounds. Now, on this slide, I say oftentimes it's the weight of the object pushing it against the ground or against the surface of the desk, but that's not always the case. Say, for example, the surface or the desk surface was at an angle for some reason. Well, then at that point, the normal force would not be equal to the weight. It would be equal to a portion of the weight that is perpendicular to the surface of the desk. And so there's some more math that goes into that, some trigonometry. That's probably above what we would be doing in this course. But for us today, what we need to know is that it's just the force that is pushing two objects together. So in this section, we're going to do an activity where we are going to determine what the static coefficient of friction is between various materials. Now, before we get started, there's going to be some things you'll need to come up with to do the activity. First, you need to find a small box, like a cardboard box, something maybe the size of a box that a bar of soap comes in. And you're going to need to find something to put in the box that's going to act as a weight. So maybe like some nuts and bolts or anything you can find that you can put inside that box. But you don't want it to be too heavy. So you need to add that weight to the box, but you don't want so much weight that it's going to deform the box. The next thing you're going to need is something that you can use as a ramp. The thing that you find needs to be about 1 to 2 feet in length. This could possibly be a piece of cardboard or a small piece of plywood or a 2x4. Maybe have your mom and dad or guardian help you find something, and if you need to, have them help you cut something to length. The third thing you're going to need is a tool to measure the angle of this ramp that you just created. So you could possibly use a protractor or an angle finder. Or if your mom or dad or guardian has an app on their phone that can measure angles and degrees, you can use that as well. You're also going to need to find 3 to 5 different pieces of materials that you can attach to the surface of your ramp. So a couple of ideas that you could use might be sandpaper, cardboard, notebook paper, maybe some wax paper or some aluminum foil. Now get creative. You can use any type of material you want, but it needs to be able to attach flatly to the surface of your ramp. Now, one thing I want to point out is that we want to use an attaching method that's not going to destroy the material that you selected. So try using maybe some Scotch tape or a stapler or something, but we don't want to destroy that material because we're going to use it in a later activity. So pick your first piece of material and attach it to your ramp. And then, secondly, place that box on that piece of material. Now, slowly raise one end of the ramp until the material first starts to slide. Now, you may have to do this several times to capture this, but you want to measure the angle of the ramp at the point when the material first starts to slide. This angle is going to be measured in degrees. Now, that angle is what we're going to record in your notebook, and we call that angle the angle of static friction. Now, do this for each of the pieces of material that you picked out, and in your table, document for each piece of material what that angle of static friction is. Now, the next thing we're going to do is use that angle of static friction, and we're going to calculate what the coefficient of static friction is. Now, for this part, you may want to get one of your parents or a guardian to help you, because you're going to need to open a Microsoft Excel spreadsheet or some other similar type of spreadsheet, and we're going to do some calculations. Now, if you don't have access to a computer or to an Excel program, you can do this calculation by hand using just a basic calculator. Now, that calculator needs to have some trig functions. And again, you may have to get your mom or dad or a guardian to help you with that calculation if you've never done trigonometry before. So, open the Excel spreadsheet. In column A, list out your materials. Now, the first row in our table, you're going to use that as a heading. And so just put the word materials in the first row of your table. And then starting in row 2, list out all of your different materials. So if you had cardboard, for example, you might put that in row 2. If you had aluminum foil, put that in row 3, so on and so forth until you have all of your different materials. Now, in column B, in the first row, you're going to make that a heading and call that the angle of static friction. And then for each of the rows in that column, put the angle of static friction that corresponds to the material that you have in column A. Now, in column C, put a heading in that column and call it the coefficient of static friction. And in that column, we're going to enter a formula. So again, you might want to get your parent or a guardian to help you with this. Enter the formula as you see it on the screen. So it's going to be the tangent of the angle of static friction in what we call radians. So radians is just another unit that we often use to measure the angle. This would be similar to the unit of degrees that you may be familiar with. So you've often heard someone say maybe 45 degrees or 60 degrees. Well, there's a corresponding value for each one of those degrees that we measure angles in using radians. So enter that formula into the spreadsheet and do that for each one of the rows corresponding to each one of your different materials. And the result of this formula is going to be the coefficient of static friction for the materials that you selected. And that is how we come up with the coefficient of static friction. Now, at this point, we've talked about the coefficient of static friction, and we've also talked just a little bit about the coefficient of dynamic or kinetic friction. Now let's talk a little bit about rolling friction. So what is rolling friction? Well, rolling friction is similar to static friction. So in static friction, we were looking at objects that were sliding against each other. And in rolling friction, we're looking at objects that roll against each other. So in static friction, we talked a little bit about how one example of static friction is the friction of a tire against the surface of the ground. We can also look at the friction or the resistance of movement that tire generates to prevent a car from rolling forward. And so we often call this the rolling resistance or the rolling friction. So looking at the screen, one thing you might notice is that the calculation for rolling friction is almost identical to that of static friction. It's just that we use the coefficient of rolling friction. So we still use the same normal force, just like we did with static friction, but we use the coefficient of rolling friction. So for this section B, we are going to recreate the experiment that we did with static friction, and now we're going to do it with rolling friction. So in this experiment or this activity, take that box that you used in activity A and get creative and come up with a way to attach some rollers or wheels to that box. So maybe use some straws or yarn spools, or if you've got any old toys that you can steal some wheels off of, attach those to the box and then recreate that same experiment by putting the box on each of those different pieces of material that you used in activity A, and record and document the angle of when the box starts to move. And so in this section, we're going to refer to that angle as the angle of rolling friction. And again, that angle is going to be measured in degrees. So using that same Excel spreadsheet that we used in activity A, create another column and put in the degrees for rolling friction in column D, and put a heading on that column just like we did on the other columns and call it the angle of rolling friction. And again, and in this column, recreate that same formula that we used in column C, but just do it in column D. So again, that's the tangent times the angle in degrees, but converted to radians. And we do that using the radians function in Excel. And so the result of this formula is going to be the coefficient of rolling friction. So what I want you to think about, and the questions I want you to ask yourself, is why is the static and the rolling resistances different? Why are the static and rolling resistances different for different materials? And why don't rollers or wheels eliminate all of the friction resistance? And I want you to think about if there's any other differences that you can think of between static and rolling resistance, and anything that you might point out or observe. Activity C is called Clip Mobile Design Team. And in this activity, we are going to design a car that is going to roll down the ramp. Now we're going to have a competition and we're going to see who can design a car that will roll down the ramp and coast the farthest distance. So there are going to be some design constraints in this project. The first constraint in this project is the performance constraint. So as I said, we want to design a vehicle that will overcome friction and roll freely down a ramp and coast as far as it can go. The second constraint is a capacity constraint. So the vehicle must be able to carry 4 boxes of paper clips. So these paper clips are just a small box of paper clips like you would buy from Office Depot. So this is a 100 count box of just small standard paper clips. So one of these boxes weighs about 1 3/4 of an ounce, and one box is approximately 2 3/4 of an inch by 1 3/4 of an inch by 3/4 of an inch. And so your car is going to need to be able to carry 4 of these boxes. Now keep in mind, not only does your car need to be able to carry those boxes by supporting the weight of the boxes, but if you happen to stack the boxes, you're going to need to have some way to make sure that the boxes also stay on your car. So keep that in mind. Now, if you don't have any of these boxes at home and you want to test your car, don't feel like you have to go out and buy boxes of paper clips. Just find something else in your house that weighs approximately the same weight and is approximately the same size, and then you can use those to do your testing with. The third constraint is what we're going to call a complexity constraint. So the car that you design needs to use at least 5 different kinds of materials. So for example, a straw may be one type of material. A dowel rod may be another type of material. So any of your materials, it needs to use at least 5 different types of materials. The next constraint we're going to have is what we're going to call an efficiency constraint. So we want to use at least 5 different types of materials, but we don't want to use any more than 10 different types of materials. So at least 5, but no more than 10. So that is one of your design constraints. Now, the last constraint that we're going to use is a budgetary constraint. So oftentimes in engineering, not only do you have to come up with a machine or a system design to overcome a problem, but oftentimes you also have a limit of how much money you can spend to solve your problem and make your design. And so we are going to implement a budgetary constraint in this project. So your budgetary constraint is going to be that your vehicle can cost no more than $35. Now, this is not 35 real dollars. This is 35 play dollars. So if you've got an old Monopoly game at home or something, you can use that as play money. You're going to be given $45 in play money to spend on your project, but your goal should be to not spend more than $35. Now we're going to get our parents to help us out with this, and your parents are going to act as your store's keeper. So parents, help find different materials and things. And one of the options that we're going to do is we're going to offer from our parents' store a $10 initial startup bag of supplies. So you can see on the screen here all of the different parts that you can buy for $10 to get your design started. Now, parents are welcome to sell you additional items. So here's a list of different items that you can buy. And parents, if you need to add to this list, if you have items that are not on this list, feel free. Just use the pricing within this list as a guide, and your parents can set their own price. Now, you don't have to use the startup package. That's just an option, but if you don't want to, then you'll have to buy each of your individual items separately. Now, one of the things that you're going to want to put in your notebook is what we call a bill of materials. And so in this bill of materials, you want to log all of the parts that you're using in your design and how much of each of the parts you're going to use. So you should have a table in your notebook, and one column of the table should be a description of what you're using. So, for example, if you have a binder clip in your design or in a drinking straw or a rubber band, list each of those items in your table. And then in the next column, document in your bill of materials the quantity of each of those items you used. So maybe if you used 4 binder clips and 2 rubber bands and 2 drinking straws, you would put that quantity in the second column. And then in the third column, you would document how much does one of those items cost. So a binder clip would be $2, a rubber band would be $1. And then in the last column, put the total cost that you spent. So if you used 4 binder clips, then your total cost would be $8 spent on that piece of material. And so document that inside of your notebook. Now, throughout the design process, I want you to go back and remember what you learned in Junk Drawer Robotics 1, where we went through the design process. And I want you to document your design process and all of the different concepts that you may have come up with. I want you to document those in your notes. And then once you come up with that final design, make a print for your car and be detailed with all of your parts, with your print, how you're going to fasten those parts. The same way that we made a print in Level 1 robotics, I want you to do that same type of print for your Clip Mobile design. And you'll bring that print and bring all of your materials with you to our in-person meeting. And then that's when you can actually build your car. And then once everyone is done building their car, we'll have a competition to see who wins. So there's going to be a scoring system based off of the design constraints that we talked about a few minutes ago. So when we score your car, the way the scoring is going to go is you'll be scored based off of the performance. So when we look at your car and we roll it down the ramp, you're going to get 1 point for every inch that the car coasts up to 60 points. So if your car rolls 60 inches, you'll get 60 points. If it rolls 37 inches, you'll get 37 points. And we'll round that down to the inch. So if it goes 37 and a half inches, we'll round that down to an inch. On the capacity portion, can your car carry 4 boxes of paper clips? So if yes, you get 10 points, and if no, you'll be awarded 0 points. On the complexity portion, we're going to look and make sure that you used 5 parts. So for every different type of part you used, you'll get 2 points. Now, even if you don't use the 5 parts, you'll still get 2 points for each part. But your goal is to get at least 5 parts. Now, on the efficiency portion, we wanted to minimize the overall number of parts used. So if you remember, your goal was to not use more than 10 different types of parts. So for every type of part, over 10 total different types of parts used, you'll be penalized 1 point. And then for the budget, we'll simply look at your bill of materials and see if you were over budget or if you were under budget. So for every dollar under $35 that you use to build your car, you'll be awarded 1 point. However, for every dollar over budget that you go, you'll be penalized 2 points. So this is very common in industry. When we're doing projects, oftentimes engineering managers are happy that you completed a project under budget, but oftentimes they get very angry if you go over budget. So that's one thing to always keep in mind. And this is the end of our first session. I will send out an email to all of the parents and we will get an in-person meeting scheduled for our first session. In section 2, we're going to do module 3. So in module 3, we're going to focus on gears, and more specifically, gear ratios. So what is a gear? Well, gears are wheels with teeth on them that slot together and are constrained to move together so that when one wheel is turned, the other wheel turns as well. So if we look in the picture on the screen, we can see that there's all kinds of different gears. And what we're going to focus on are what we call spur gears. And so gears in general manipulate how the speed or power from an input shaft can be manipulated and delivered to an output shaft. And so gears can do several different things. 4 of the main things that they do is they can increase or decrease speed. So if you have an input shaft that is running really fast and you want to slow that speed down, you can do that using a set of gears. Gears can be used to increase or decrease torque. And so if you need to increase the power output of a system, you can do that through gears. So if you remember back in Junk Drawer Robotics 1, where we were looking at levers and we talked a little bit about mechanical advantage. Well, gears are how we build mechanical advantage in rotating systems. Gears can also be used to change the rotational direction. So if you have an input shaft that is turning clockwise and you want an output shaft to turn the opposite direction, you can do that by using gears. And gears can also be used to change the orientation of the output shaft compared to the input shaft. So we're not going to talk too much about that here, but if you look in the picture, you can see some of the different gears that might do that. So the bevel gear, for example, or the miter gear, you can see how you have an input shaft that would come in on one gear and the output shaft would be at a different angle compared to the input gear. So there's all kinds of different things that we can do with gears when we design machines. But one of the things that we're most interested in is developing what we call the gear ratio. So what is a gear ratio? Well, the gear ratio is a comparison of one gear to another. So typically we use the gear ratio to determine how much mechanical advantage we can get out of the gears, or how much increase or decrease in rotational speed. And so if you look at the screen, we can see that gear ratio, here represented by GR, can be represented by several different fractions. So the first of those fractions is we can look at the input rotation, or the rotation of the input shaft compared to the rotation of the output shaft. We can look at the speed of the input shaft compared to the speed of the output shaft to get the gear ratio. We can look at the diameter of the output gear and compare that to the diameter of the input gear and we can use that to get the gear ratio. Or we can count the teeth on the output gear and compare that to the number of teeth on the input gear. And so we can see in this picture where we have an input gear, or gear number 1, or gear A, that has 25 teeth. And we have an output gear, or gear 2, or gear B, that has 75 teeth. So if we look at the equations that we just talked about, we're going to take the number of teeth of the output gear, or gear B, and divide that by the number of teeth on the input gear, or gear A. So 75 divided by 25 gives us a ratio of 3 to 1. So we would say that the gear ratio between these two gears is 3 to 1. So the activity that we are going to do for activity I is we are going to measure the gear ratio on a mountain bike. So if your mom and dad or guardian have a mountain bike that you can use, see if you can borrow it from them. Or if you have just a regular bike, we can do it on a regular single speed bike as well. Now on this activity, you're going to have your parents' help, okay? Because we're going to have to manipulate your bike, and it may be a little too heavy, and plus I don't want you to get your fingers pinched. So this is definitely something that you'll want to do with some adult supervision, okay? So what you're going to do, if you have a parent's bike and it's capable of shifting gears, so a lot of times mountain bikes will be 10 speed or 12 speed or 21 speed bikes. There's a lot of different variations. So whatever variation of the bike that you have, if it's capable of shifting gears, put the gear in the lowest gear that the bike has. And then flip the bike upside down so that it's sitting on the handlebars and on the seat, so that you can rotate the foot pedals by hand. Now put a piece of tape around the rear wheel so you can see what position the rear wheel is in. And what we're going to do is we're going to rotate the foot pedal by hand one turn, and then we're going to calculate the number of turns of the rear wheel. So what you'll want to do to start is you'll want to position the foot pedal so that one of the pedals is in either the straight up or the straight down position, and then rotate the back wheel so that the tape is in maybe the 12 o'clock position, and then slowly rotate the foot pedal by hand. And while you're doing this, you'll want to put one hand on the wheel so that there's a little bit of drag on the back wheel. And then as you slowly rotate the foot pedal, you'll want to count the number of rotations of the rear wheel. And so when you've made one rotation of the foot crank, you should be able to have a visual count of how many times the rear wheel went around. So if it went around more than one time, that'll be a number greater than 1, obviously. Or if it was less than 1, then it's going to be some fraction. So if the wheel lands somewhere other than the 12 o'clock position, you'll just have to estimate, right? So 25%, a half, or 3/4, or 1/8, 3/8, 5/8, 7/8 of a turn. You probably don't need to be much more accurate than down to the eighths, but just be as accurate as you can and just kind of make a visual count. So, for example, a number like 1 5/8 might be a result, or 7/8 might be a result. And then once you've done that, shift the gear of the bike and put it at some gear that's in the center of the range of gears. So if it's a 12-speed bike, put it in gear 6, right? Or maybe put the front, usually mountain bikes will have 3 gears on the pedal and maybe 3 or 4 on the axle. So maybe put the front chain in the middle sprocket and then put the rear chain somewhere halfway through the range. and then repeat this again. Do one full rotation of the foot pedal and count the number of turns of the wheel. And so for each one of these positions, log that in your notebook. For the input will be 1 associated with the lowest gear, and then the same thing with a mid-range gear, and then go to the very highest gear that you can put the bike in. And again, 1 rotation of the input and count the number of rotations of the wheel and put that in your output column. And then go back to our calculation that we used for rotations to determine the gear ratio. So if you remember, that calculation is the input rotation divided by the output rotation. So take the number of input rotations will be 1 because we only rotated the foot pedal 1 time, and then divide that by the number of times that the wheel turned, and that will give you the gear ratio for each of those gears that you had selected for your mountain bike. So if you don't have a mountain bike and you have maybe a kid's bike that only has 1 gear, then don't worry about doing it for several gears. Just do it for the sprockets that exist on your bike and just calculate the gear ratio for the 1 sprocket that you have on that bike. That'll be perfectly fine. So for example, I did this on one of our mountain bikes, and I will show you the results that I got. So I didn't do 3 ranges, I just did the highest and lowest gear on our mountain bike. And so let me show you the results that I got. So for the first example, I did 1 rotation of the input gear, and I counted 7/8 of a rotation on the output gear. So what gear ratio would that give us? Well, when we count the rotations, it is the rotation of the input divided by the rotation of the output. So this would be 1 divided by 7/8. Or more precisely, we could reduce that down and say 8 to 7. So the gear ratio for the lowest gear of that mountain bike would be 8 to 7, or 8 rotations of the input for every 7 rotations of the output. And then I shifted the bike into the very highest gear that it had available, and 1 rotation of the input, or the foot pedal, generated 3 rotations of the output. So the gear ratio of the highest gear on the mountain bike would be 1 to 3. So we could also put that in a decimal format, and we could say that that gear ratio would be 1/3, or 0.333, right? So one of the drawbacks of looking at the rotations is that's a visual approximation, right? So there's going to be a little bit of error involved. Now, a more precise way of doing that calculation would be to count the teeth on the sprockets. And so I did that. And let's look at the results that I got by looking at the teeth. Now remember, when the teeth calculation is not the input over the output, when we look at the teeth, that calculation is the output gear divided by the input gear. So the results that I got for the lowest gear, there were 24 teeth on the lowest gear of the front sprocket, and then there were 28 teeth on the lowest gear of the rear sprocket. And then on the highest gear, there were 41 teeth on the highest gear and 14 teeth on the output gear, or the gear on the wheel. So if we look at the difference between the visual approximation and the counting of the teeth, which is a more precise calculation, we can convert those ratios into decimal and compare the two. So when I did a visual approximation, the 8 to 7 results in a value of 1.14, but when I count the teeth, I get a value of 1.16. So we see that it's pretty close, but there's a little bit of error involved when we try to just eyeball it. Now, when I look at the highest gear, I had a 1 to 3, which is 0.33. And when I counted the teeth, I took 14 divided by 41 and got a value of 0.341. So again, pretty close, but we need to understand that when we try to eyeball things, it's a little bit of error, whereas counting the actual teeth on the sprockets or the gears results in a much more precise result. So for you, I would recommend just doing a visual approximation. If you want to try to count the teeth, that's fine. But again, be very, very careful by putting your fingers around the chains and the sprockets, because I don't want you to get your fingers pinched. And make sure that your parents are there and watching what you do, okay? And so I want you to record your results in some tables and put those in your notebook, okay? And again, be very, very careful and don't do this without a parent's supervision, okay? So now that we have a good understanding of gears and gear ratios, let's move on to something just a little bit more complicated. Let's talk about gear trains. So in gear trains, we use multiple layers of gears to obtain various gear ratios. And we do that by incorporating something called a compound gear. So what is a compound gear? Well, a compound gear is a situation where you have two gears that share the same shaft. So if you look in your gear kit, you will see several little plastic gears that look similar to the picture on the screen. Here you can see where there is a smaller gear on the center and then a larger set of gear teeth on the outer edge of the gear. And both of those gears share the same shaft. So that gear kind of acts as a single unit, but yet it has two different gears associated with it. So let's look at an example in the picture here. Here we see an input gear, gear A, that drives the outer gear of the compound gear, which we've identified here as gear B. And then the inner portion of the compound gear, identified here as gear C, acts as the driver for the output gear, which we call gear D. So the input gear A has 10 teeth. The outer portion of the compound gear has 40 teeth. The inner portion of the compound gear has 20 teeth. And then the output gear, gear D, has 50 teeth. So when we calculate the overall gear ratio of the gear train, we take each of the gear ratios and we multiply them together. So let's look at this example here. We have two gears that are mated together, gear A and gear B. So here A is the input gear or the drive gear, and B is the output gear or the driven gear. So if you remember back for our gear ratio calculations, when we are looking at teeth, the ratio is the output gear divided by the input gear. So for this example, the gear ratio between A and B would be 40 teeth divided by 10 teeth, or 4 to 1. And then we look at the second set of gear interactions, which is the interaction between the smaller gear of the compound gear, which is gear C, and the output gear of gear D. So here, C is the drive gear or the input gear, and D is the driven gear or the output gear. So again, the gear ratio between C and D would be 50 divided by 20. So 50 teeth divided by 20 teeth. So that's a 2.5 to 1 gear ratio. So to get the overall gear ratio of the gear train, we would multiply the gear ratio between A and B with the gear ratio between C and D. So 4 to 1 multiplied by 2.5 to 1 gives us a gear ratio of 10 to 1. So when we look at this, we can see that the input gear of gear A is going to rotate 10 times compared to that of gear D. So one thing to notice about a gear train is that you're not limited to just 3 gears as we see in this example. Gear trains can have any number of gears in them. So there's really no limitation to how you can design your gear train. And by adding multiple compound gears within our gear train, we can really manipulate the gear ratios, and we can get really aggressive ratios, things on the order of 100 to 1 or 500 to 1 type of gear ratios. And so you can imagine the amount of mechanical advantage we can get when we have extremely large gear ratios in our gear trains. So for activity K, we are going to be building some gear trains. So for the first part of activity K, you're going to use the gears from the gear kit that you bought from Amazon, or from the gears that you possibly stole from some old toys. So the first thing you're going to want to do is sort your gears somehow. So you're going to need to find a good way to organize your gears so that they don't get mixed up with each other. So for example, get an egg carton or maybe a piece of cardboard with some pins or something of that nature. And you're going to want to sort those gears out into driven gears and drive gears. So everything I'm going to work off here are going to be based off of the gears that come in the Amazon kit. So in that Amazon kit, there's some gears that will slide freely over the shafts that are included in that kit. And then there are other gears that will have a press fit onto the shafts. So the gears that slide freely, those are what we're going to call idler gears. And also some of those are compound gears. So sort those out. And once you have all of those gears sorted, you're going to want to count the teeth on the gears that you're going to want to use in your drivetrain. So when you sort those gears, count the teeth, and then, for example, if you're going to organize your gears in an egg carton, you might put one gear in each spot in the egg carton and then write the number of teeth that are on that gear on the egg carton. Because the gears are so small, you can't write on the gear, so you have to have some way to kind of document how many teeth are on each gear. Another idea you could use is if you've got some wire tags that you could put through the whole of the gear while you're not using them, and then write down how many teeth are on the gears. But so however you want to do that, you can get creative, but at the end of the day, you're going to want to know for each gear that you intend to use in your gear train, how many teeth are on those gears. And so once you have all of that stuff documented, I want you to design a gear train. So this gear train doesn't really have to accomplish anything, but I just want you to go through the exercise of identifying an input gear and then determining which gear on the compound gear you're going to drive, and then which one of those gears are going to act as the driven gear for the next gear in the gear train. And then build up a series of gears in your gear train, kind of just like we did in the exercise on the previous screen. And once you've configured a set of gears that you want to use, I want you to calculate what the gear ratio is for the gear train that you've configured. And so I don't want you to build this gear train yet, but just theoretically calculate what you predict the gear ratio to be. And so I want you to do 2 specific gear trains. Now you can do more than that if you want, but I want you to do at least 2 gear trains. So for your first gear train, I want you to design it without using any compound gears. We can just use intermediate gears. Again, we call those idler gears, but don't use any compound gears. And then in the second gear train that you design, I want you to incorporate the compound gears into your design. So, for example, on your first gear train, your gear ratio or your overall gear ratio of your gear train will be the gear ratio of gear 1 to gear 2 times the gear ratio of gear 2 to gear 3 times the gear ratio of gear 3 to gear 4, so on and so forth. And then again on your second design, the gear ratio will be gear 1 multiplied times the whichever gear of the compound gear you designate as the driven gear, and then the drive gear from the compound gear to gear 3, and then so on and so forth, just the same way that we did in the example on the previous screen. And so do that and calculate your gear ratio. And then when we get to our in-person meeting, we will take the gears that you used in your calculation and we will physically build that gear ratio, and then we will test similar to the way that we did on the bike. We will look and see what the gear ratio is by looking at the number of turns of the input gear of the gear train compared to the number of turns of the output gear of the gear train. And we will see experimentally if your calculations were accurate or not. And so that's what we're going to do in our last in-person meeting, is build those gear trains. So here is an example of a gear train that I built. And so this is what we'll do in our in-person meeting. I don't know if you can see it on the video or not, but here you can see I've built up a series of gears on this board using the pins and the gears that were included in that set of gears from Amazon. And you can see that when I turn the input gear, all of the gears rotate, and I can count the number of rotations of my input gear and compare that to the number of rotations of my output gear to determine the overall gear ratio of that gear train. So now that we've learned a little bit about gear trains, I want you to think about where you might find a gear train out in the real world. So one example that we can think of might be in your mom or dad or guardian's car, right? So we've all ridden in a car down the highway. What is one thing you notice when you ride in that car and you accelerate from a stop up to highway speeds? If you listen closely, you can hear the transmission shift gears as the car goes faster and faster down the road. And what is happening inside of that transmission is we are changing gears within the transmission to change the overall gear ratio of the transmission to allow the car to drive faster and faster down the road. So that is one everyday example of where we might find a gear train. So I'd like for you to think about other areas in the world where you might find a gear train and write some of those ideas in your notebook and bring those to our in-person meeting, and we will all share the ideas that we came up with of where we think we might find gear trains. So as I said, we will build those gear trains in our in-person meeting, and then we will compare the gear ratio of your physically built gear train to the theoretical calculation of the gear ratio that you calculated based off of the number of teeth of the gears that you used. So remember, I want you to document in your notebook the process that you used to design this gear train, and document your calculations and bring all that stuff with you to the in-person meeting, and we will get your gear train built and see if your calculations were correct. And so that is the end of our second session, and that is the end of our Junk Drawer Robotics Level 2 course. I hope everyone learned a little something from this, and I will send out email notifications and get a time scheduled for our in-person meeting. Again, if you have any questions or you need any help, feel free to reach out to me, and I will help you in any way that I can. And I look forward to working with you all this year.